in this class we will do a couple of problems related to converging nozzles. Okay. So, first let us try to understand the importance of critical pressure. So, if I have a tank with a converging nozzle, I have a P0 here, P ambient here, P exit here. Okay. So, the exercise is to show you the importance of P star. So, first case, we will assume PB to be 1 bar. In this problem, PB is 1 bar. So, I have a high pressure cylinder and it is going to eject through this nozzle. So, I am not talking about the area or area ratio of the nozzle, I am just going to talk about the pressure ratios. Suppose the first question, if my P0 is 1.5 bar, what is the Mach number at the exit? Okay. The question is to find the Mach number at the exit. So, I have P0 by P. So, my P B by P0 is 1 by 1.5, which is 6.7, and the Mach number associated with this, I look at the tables. So, I take the isentropic tables, look for gamma equals 1 because I assume the fluid to be air inside the cylinder and the process is isentropic. So, what I have here is an isentropic flow. So, this P0 what I have inside the tank is also the P0 throughout the nozzle. So, the P0 here inside the tank is constant here. If this is my section 1 and this is my section 2, P01 equals P02, T01 equals T02 and A1 star is equal to A2 star or any other section, this is true. With this assumption, I have taken the ratio Pb by P0 and found to be 0.71, from which I can find a Mach number, either use the tables or use the relation. So, my P by P0 is 0.67. I look at the isentropic tables for gamma equals 1.4 and I find P by P0 1.67 is going to be 0.77. 0.77, which means if I plot my pressure, this is my P0, Pb is 1 bar, this is 1.1 bar, P exit is also going to be and this is a subsonic flow, which means P exit is less than. So, when it reaches P star, you are going to have this value. Now, if in the second case I keep Pb same and I increase my P0, I have a tank with a larger pressure ratio. So, let me put it as 1.89 bar. So, I have a tank with gamma 1.4 air and the process is isentropic. I want to find the exit Mach number. Okay. P0 1.89, PB 1 bar, isentropic flow. So, P0 is constant, T0 is constant, A star is constant. With this assumption, I can write PB by P0, which is 1 bar by 1.89 bar, which is 0.528, and the Mach number at the exit associated with this pressure ratio is 1. So, I have a sonic condition here, m equals 1, and if I plot I have PB equals 1 bar, P exit equals PB, which is also equal to your P star, and your P0 is 1.89. Now, in my third exercise, I have my PB 1 bar, P0 2.5 bar, I have isentropic flow, P0 is all up to this. I have PB 1 bar outside the nozzle in a converging nozzle. Question is to find M exit. So, in the previous case, since M equals 1, this is also your choked condition. So, any pressure higher than this or any pressure smaller than this ratio is going to be choked condition. So, that is what we had seen in the previous lectures. If I have already reached my choked condition at the exit, where your P exit equals PB, any condition smaller than this would give you this. So, your P by P0 is P exit by P0 is smaller than your P star by P0 for the choked condition. Okay. So, now instead of reducing the PB, what we have done is we have increased our P0. So, P star by P0, we know it is 0.528, and now the PB by P0 here P exit is same as your P star, which PB by P0 should be less than your P star by P0. P exit is same as your P star because that is not going to change. Even if you decrease your PB from now on, your P exit is not going to change. What is happening outside the nozzle is going to change. Okay. So, this pressure PB keeps going down. So, your PB by P0 is now 1 by 2.5 which is 0.45, 0.4, oh 2.5, okay, 0.4. So, the Mach number associated with this is, if you look at the gas tables, 0.4, the Mach number associated with this should be supersonic. .22. Since there is no diverging section, you cannot get this value. So, this is not the exit Mach number. This is the Mach number for associated with this pressure ratio. But after the chalked condition, whatever you do, the exit Mach number is not going to change. Exit Mach number is always going to be 1 after once you reach your chalked condition. So, once your pressure ratio has reached your chalked condition, whatever you do after that to decrease your pressure ratio, your exit Mach number is still 1. But this is technically, if you had a diverging section, you would have got, or for this pressure ratio, this is the Mach number which you can attain. We will discuss about this, what happens, but this is not the exit Mach number, that is what we are trying to give. So, the P star, this ratio, or the critical pressure ratio for air with 0.5 to 8 is very important, and that is where you demarcate between the possibility of having a supersonic flow or a subsonic flow. So, if I have a tube, say for example bicycle tire which is punctured, you are going to get the pressure ratio is very small, you are going to get only subsonic flow. Whereas, if you have a puncture in your say big tire in a truck or a bus, then you are going to likely to get this pressure ratio, but the exit Mach number is still 1. So, you may get this Mach number after the exit if you appropriately do something, but this is the exit Mach number. Okay. So, the supersonic flow that you are going to see in the bus tire puncturing is something which we are going to discuss after discussing the converging diverging nozzle. So, the jet is going to do an area change, and that jet you would see the supersonic shocks and other things which you can, which is a everyday life example for a supersonic flow, which is just the puncturing of your bus tire. Okay. So, the exit Mach number is still 1 there, it is not going to increase, okay, because it is already chalked. Okay. Now, we go to the next question. So, you could do this Mach number identification from this pressure ratio using gas tables or with the equations which we have already written, which is what? Which is P by P0 equals 1 plus gamma minus 1 by 2 to the power gamma minus 1 by gamma. So, you could use this equation or the gas tables to get this formulation, the Mach number associated with the pressure ratio. So, next question is, I have a nozzle inlet area is 0.1 meter square and the contraction ratio is A1 by A2 is 5, V1 is 5 meters per second, P1 is 100 kilopascal, M at exit is 1. Find V2, P2 and m dot. Assume isentropic. Okay. If you assume isentropic flow, we can use the equations which we have derived, otherwise we cannot. So, we will assume the isentropicity. So, the moment you assume isentropic flow from section 1 to 2, there are 3 things which you need to write. First thing is P01 equals P02, T01 equals T02 and A1 star equals A2 star. Okay. So, if I know my A2 by A2 star or P02 by P2 or T02 by T2, I can get my M2. Okay. So, we are given A1 and A1 by A2 star. So, let us try if we can get A2 by A2 star from this relation. Okay. So, A1 by A2, I can rewrite it as A1 by A1 star into A1 star by A2. Since A1 star is also equal to A2 star, I can write this further as A1 by A1 star into A2 star by A2. Wait a minute, we are already given M2 equals 1. So, I can get the appropriate A2 by A2 star from where M2 is 1, which is 1. So, I would go further. So, my A1 by A2 is 5 equals A1 by A1 star into 1, correct. So, my A1 by A1 star is 5. Okay, from which I can get M1. Which if you look at the tables, you would get it to be from tables or from the equation, if you can remember the equations. Okay. Ideally, you should get it from the tables, isentropic table when M1 is. So, if the question is to find V2 and P2, but let us go ahead and do the temperature calculation. So, if I have M1 equals 0.12, which is my V by A, 0.12 equals V is 5 meters per second. 5 meters per second into root gamma r T1. So, I can get T1 as 5 by 0.12 root of 1 by 1.4 into 287 for air, which is approximately 4.32 Kelvin. Is this correct? Okay. Now I will go ahead and write to find T2 from this particular ratio, which, because the stagnation temperatures are same, I can write T0 T2 by T02 into T02 by T1. Now T1 and T02 and T1 are the same, so I write T01 T2 by T02 into T01 by T1. So this I should get from Mach number 2, this I should get from Mach number 1, which I again look at the isentropic tables. T02, this ratio for Mach number 2, which is 1, and this is for 0.12, which is 0.834 by 0.9971. So, I look at the tables for gamma equals 1.4 and get these ratios, which is and I get T2 as this ratio 0.834 by 0.9971 into T1, which we have just now found 4.32 Kelvin. So, your T2 is 3.61 Kelvin. Okay. Now, we know the exit Mach number is 1, which means the nozzle is choked. So, M2 is 1. So, your V2 is A2, which is root of gamma or T2, which is root of 1.4 into 287 multiplied by the temperature just now we found, and your V2 is going to be approximately 38 meters per second, 38.1 meters per second. Now, similarly, you can find P2 by P1 and substitute the values that we know. So, I will just rub T and write P, P2 by P1. So, this is P2 by P02 multiplied by P02 P, since P02 is same as P01, I replace P02 by P01 by P1. So, I should get this value from m equals 2, this value from m equals 2. Remember, this 2 is at the exit, not the ambient pressure that is happening at the exit. So, P2 is this. What we have is something different. Okay. So, what we are calculating is P2 at the exit of the nozzle. There is no way we can find this. We only know that that should be less than P exit. So, I do this process and I compute similar values, which is Mach number 1 is 0.528 divided by 0.989 for m equals 0.12. Again look at the isentropic tables where gamma equals 1, look for m equals 1, get the pressure ratio, look for m1 equals 0.12, take the pressure ratio. This is the inverse. So, that is why we divide this here, and here the P2 would be 0.528 divided by 0.989 into P1 is 100 into 10 power 3 Pascal. So, your P2 is 53.3 kilopascal. So, essentially we can get all the properties that is happening inside the nozzle if your area and area ratios are given, and some of these quantities are given using the tables or from the equations. For example, this you could actually compute from equations also if you remember it. Okay. Otherwise, look at the tables and get the Mach number for the given gamma value of 1.4. Now, it has become more easy to find your m dot. M dot is rho A V. So, one area we know is the inlet area. This has to be constant. So, we will use that area. So, it would be rho 1 A 1 V 1. So, we know A 1, we know V 1. So, only thing that is missing is rho 1, which we can write it as P 1 by R T 1 into A 1 V 1, assuming ideal gas equation to be valid here. So, this is 100 into 10 power 3 divided by 287 into T1 we have found out to be 4.32 into area is 0.1 meter square into 5 meters per second. This will give me a value of 40.33 kilogram per second. Okay. So, we will do the third question, again converging nozzle. So, the inlet stagnation pressure is 110 kilopascal, T0 is 300 Kelvin, the inlet area is 0.01 meter square. Find mass flow rate if m at exit is 0.8. That is your first question. Second question, if at m exit is 1, we find the maximum mass flow rate. The area ratio also you would need. The area ratio A1 by A2 is 4. Okay. Okay, so if your M exit is 0.8, assume isentropic as before, isentropic flow. So, the moment I write isentropic flow, I write this 3 equalities. Since I know M exit, I can get my A1, A2 by A2 star for M exit, which is, I look at the tables for 0.8. So, I should be careful to pick the right chart. Gamma equals 1.4, M equals 0.8, I will have A by A star to be 1.038. M8 is 1.038. Okay. So, your A star is smaller than your A2, okay, which means that you have to reduce further to get M equals 1, that is the meaning of A2 star. Now, from A1 by A2 equals A1 by A1 star into A2 star by A2, from which I can get A1 by A1 star, which, so this is 4, this is multiplied by 1.038, correct, A1 by multiplied by this. Yeah. 4.152, from which I can get my M1. So, if I look the area ratio 4.15, area ratio 4.15, I should be careful here because I will have two solutions, one is supersonic, one is subsonic. So, my supersonic value is, I will write 4.15, so that is approximately 2.98 or 0.145, correct. Okay. So, now we have two solutions. Now, we have a decrease in our velocity here in the converging, increase in our velocity in our converging nozzle. So, if the inlet Mach number is 0.14, it would increase to 0.8. Okay. If it is a supersonic value, this will again decrease to 0.8, which is not possible because it has to cross M equals 1 somewhere inside, which is not possible. Okay. So, the supersonic flow is not possible because m equals 1 cannot be inside the nozzle. Why is that? For m equals 1, your dA has to be 0, which is not inside the nozzle. Okay. So, we will stick with the subsonic solution, which is m equals 0.145. So, that is our m. So, now if I know my Mach number, I can easily find my mass flow rate. So, my mass flow rate by area, which is my mass flux, is given as root of gamma by r into m into 1 plus gamma minus 1 by 2 m square to the power minus gamma minus 1 gamma plus 1 divided by gamma minus 1 into 1 by 2 into P0 by root of T0. So, at inlet we know all the values. A is known, M is known, P0 and T0 anyway is not going to change along the nozzle. So, I can substitute this value and find my m dot. So, your m is 0.145 and your area is 0.01. So, my m dot is, so if I know my area at the exit, if I know my area at exit, I can use my m2, but since I do not know my area at exit, I use this. Area at exit, you can find it from your area ratio. So, if your area ratio is A1 by A2 is 4, I can find my A2 to be A1, which is 0.01 divided by 4. If I know this, I can use my M2. So, for this area and this M2, I can compute my m dot, which should be the same. What is 0.635 kg per second. Okay, let us assume that is right. Okay. So, either you use the exit area and exit Mach number, or inlet area and inlet Mach number, that has to be constant across the cross section. So, you would get this. Now, the trick is when m equals 1, what do you do? Remember, this mass flow rate will be changing when you change your pressure. So, this is my Pb by P0, this is my m dot. So, when this is 1, there is no flow, and then slowly it goes up, and then it has a constant value. Okay. So, what we have found now is somewhere here, where m equals, m exit is 0.8. Okay. Now, the question is to find m dot at m equals 1. Okay. So, the conditions have changed. So, m dot will also change. So, for that, so this is also the chalked condition. So, at chalked condition, your A2 is now your A star, because A2 by A star for m equals 1 is 1. So, your A2 is also your A star. Now, A2 is A1 by A2 into A2 by A1 into A1. This is 1 by 4 into A1 is 0.01. Okay. So, that is my A2. And my M2 is now 1. So, I will substitute 1 here. So, my A here is 0.0025, M2 is 1, P naught and T naught we already know, which is 110 kilopascal, T0 is 300 kilopascal. Substitute this value, I would get my m dot as kilogram per second. Now, this is the answer to your second question. Now, the third question, to answer that, all you need to do is look at this particular plot. So, if I reduce my pressure ratio, I would reach m equals 1 at some condition, and after that the mass flow rate is going to be constant, because we have reached the chalk condition, which is the maximum possible mass flow rate through that particular area ratio. So, for that particular area you would see the maximum possible mass flow rate. So, your B answer to the C is also your answer to your B, which is what you get from here, which will be larger than what you the question for A, which is okay. So, that brings us to the discussion of maximum flow rate. So, the question is very simple. I can do the same problem by increasing my P0, which is what we had done in the previous question. Here somehow I have attained 0.8, I did not tell you how I have attained 0.8 and 1. Somehow we have attained 0.8, keeping P0 and T0 constant, and then computed the mass flow rate. Okay. So, depending on your P0 and T0, you can attain your m star. Okay. So, the important point here is A2 is also your A star once the chalked condition is reached. Okay. Now, we can actually do the problem for diverging say channel or duct as well. So, the same process. Okay. So, you can reverse the problem and do whatever it wants. So, with the same numbers, try doing this yourself, make a question yourself and put a P0, try to find what is the mass flow rate, how does the area change, how does the velocity change with the area change, and all those things. You can keep the area ratio same as this and design your own problem and do it. So, the important thing is to use gas tables to do all this. There are tables which would give you maximum flow rate also included, but this particular book does not have the maximum flow rate included in this chart. The other quantities we will use it appropriately. So, there are other tables as well. At present we have used only the isentropic flow tables for gamma equals 1.4. The procedure is same for other gammas, but we will stick to gamma equals 1.4 for convenience. Okay, thank you.